Thanks for the introduction. So the purpose of this, the presentation is mainly on direct drive machines for renewable power generation. It's not a long presentation. I'm briefly going through few applications that have direct drive machines as well as geared drive, and the rationale for having either of them. And in the later few slides, I'll also present some of the work we've done in designing electric machines for certain renewable energy applications as well. So just to start off with, I'll introduce the concept of direct drive machines. And obviously, you've heard of geared drive machines. So this is a snapshot, a summary of what we are looking at. In the left side, we have a torque speed profile. So the black curve here shows the torque speed profile that you would have for the high speed machine, and it's coupled with a gearbox and the input shaft. The combined gearbox and the high speed machine would produce this red torque speed profile. So it's a gear ratio. For example, I mentioned 5:1. So the speed would reduce, the torque would increase. On the contrary, you might have a situation where you have a machine that's producing low speed and you want to step up the speed. So you have a inverted gear ratio where 1:5 speeds up, the speed increases, and then the torque reduces. So that's the other version of the application. So in the latter one, the one to the right side, you have a high-speed machine, and high-speed machine, that's the direct drive motor. So usually if you look at a low-speed machine and a high-speed machine, the lower speed machine, we can design it to be lower weight, so it's lighter. If you want to achieve the same torque speed with a geared machine, you would need to couple it with a gearbox, which adds weight to the package. So for example, if we have an application where we need a higher torque and a lower speed, you have a high speed machine coupled with a gearbox that reduces the speed, then that would weigh more than the direct drive machine. The direct drive machine would be running at a higher speed and then lower torque, that would be producing the same torque speed profile. So this is beneficial, whereas on the left side, you have the opposite situation where you have a high speed machine that is coupled to a geared gear, and then the torque is increased, the speed is reduced. So to match the same torque speed profile, you'll need a machine that's weighing more, so that it adds more weight to the package. So that's not beneficial. However, we see that if you compare the weight of the direct drive option to the left side and the gear drive option to the left side as well, the weight difference is not that much in certain applications, but then in very specific applications, we find that the gear drive motor or the gear drive generator has certain benefits in terms of packaging. So I'll go through a couple of examples that we encountered during our projects here in Melbourne. So before I move on to the work we did here in Melbourne, I'll just briefly outline some of the renewable energy applications and the machines they use. So obviously, the most commonly heard one is wind power generation. You have two options. One is with the gearbox and a generator, and the other option is a direct drive without the gearbox. You directly couple the machine to the generator. So in this type of application, although you tend to think that the geared machine might, the gearbox plus the generator might weigh more than the direct drive machine, we find that the direct drive generator weighs more than the gearbox and generator combined weight. So that's mainly because when you go into direct drive generators, they need to be low speed. And then as a result, the weight of the generator becomes really high. However, the advantage of going into direct drive machines is the elimination of the gearbox itself. So although there's no weight benefit in weight reduction in this type of application, the reduction in maintenance requirement that helps with the application, and also the construction as well. So these are some of the advantages and disadvantages of direct drive. We have increased efficiency. So when you get rid of the gearbox, you tend to improve efficiency because you have less frictional losses, and you have a reduction in maintenance requirement, and also it performs better in variable speed conditions. If the wind varies continuously, you have a better control of the speed if it's direct drive. If it's running through a gearbox, you have other issues such as backlash and certain vibrations that happen because of the gearbox itself. So when we eliminate the gearbox, that's beneficial in certain applications such as wind power generation. However, when you look at direct drive machines, for wind power applications, they tend to be permanent magnet generators these days. So the permanent magnet generators are much more costlier than an alternative geared synchronous generator or a geared wound field induction generator. The direct drive machine tends to be a little bit heavier because the volume of magnets. So the magnets are high dense. The density is same as iron, and because you need a huge volume of magnet for high power permanent magnet machines, the overall weight of the generator is probably equal or more than the geared generator option, the package of the gear and the machine itself. So that's one of the disadvantages. So that's wind power generation. And if we look at the requirement, we need it to be beneficial. We expect the gear and the high-speed generator weight to be smaller than the low-speed direct drive machine, but it's the opposite in many of the wind turbines we find. So the other application is hydropower. Obviously, the large hydropower stations, they use synchronous generators, and they tend to be without any gearbox because we don't have the need to reduce weight, and you kind of eliminate the gearbox requirement altogether. So that's in large hydropower, it's naturally beneficial to have direct drive synchronous generators running. So that's one application that we find in Sri Lanka most often. The other option is for small hydropower, less than 10 megawatt and smaller, similar to the wind power situation. The case with wind power, the direct drive machines, with when you compare it with an option where you have a geared drive and a generator, the weight is almost similar. So there's no real advantage in weight. However, the main advantage comes from maintenance, the lower maintenance with direct drive machines. In the end, it turns out that the main selection of whether to use a direct drive machine versus a geared machine comes down to cost, where if the cost of having a direct drive machine outweighs the cost of maintaining a geared machine, then that's the key decision-making point where we have to consider. However, direct drive machines are useful for specialized applications where you need certain packaging requirements or variable speed conditions. Then the direct drive machines become much more useful. So I'll present one of the applications that we designed a machine for a vortex turbine application. So this is similar to a small hydro, but it's a very specialized turbine where the turbine itself is in the shape of a globe, and the generator was to be designed to be placed inside the turbine or this structure itself. So the turbine has a hollow part inside, and the generator needed to be placed or designed and fitted inside the turbine structure itself. So then in that kind of specialized application, we need to lower the weight as much as possible. Then in this type of application, the speed varies significantly as well. And as a result, the geared drive option becomes a bit more complicated. And the direct drive option is a bit more simpler in terms of packaging and manufacturing this type of prototype. So that's one application, and this is the stator we designed for that application. And also the generator itself is not a conventional generator. It's an outer rotor type generator where you have the stator in the middle part of the structure, and the rotor is on the periphery or the outer turbine. So the rotor is placed, the magnets are placed on the outer periphery of this inside of the turbine, and the stator sits in the middle. So the stator is stationary, and the turbine with the magnets rotate around the stator, which is in the middle. So that's like a specialized application, and that type of application requires a direct drive design rather than a geared machine. So that's one application with respect to power generation, hydropower generation. The other renewable energy application that we find geared drive machines and direct drive machines is in ocean wave power generation. So the ocean wave energy generators, we can categorize them into reciprocating devices and continuous rotating devices. So in this animation here, that's a motion that's reciprocating. It's going up and down, and then you would have a linear type generator, a linear generator that generates power of that motion. Alternatively, there are mechanical setup that could convert this linear motion into a rotary motion as well, and then you would couple it with a rotating, continuously rotating generator, conventional generator. Alternatively, you could also have a system where the reciprocation is converted into a reciprocating motion, rotary motion, which requires another type of a setup to convert that motion. So one of the projects that we were involved in here in Australia is this one. It's called a moored multimodal multi-body power offtake. So this type of structure, it reciprocates or goes up and down, and then the hinges are connected with a geared drive or a gear system, and the gear basically spins forward and then spins backward. So this type of reciprocating power absorption device, we found that if we have a gearbox coupled to a electric machine, the power generation is deteriorated by the backlash in the gearbox. So that was one of the main down points of this type of application. So in this application, the hinge in this device rotates at lower speed, and then the gearbox pretty much steps up the speed. So if it spins at 100 RPM, like sinusoidal waveform, it spins up the speed to be up to 2000 RPM. And then the generator couples to the high speed side of this gearbox. However, the power generation capability of this setup was compromised by the backlash of the gearbox. So the backlash mainly relates to the gear teeth engagement. So if you have a reciprocating motion, you have when it spins forward and then stops and then starts spinning backwards, there's a delay or a gap which needs to be compensated, so that when it reciprocates every cycle, you lose certain amount of motion because of that backlash between the gear teeth. So that kind of application, it's preferable to have a direct drive machine at a lower speed to capture the power, whereas if you have a gearbox, it kind of you lose part of the power due to the backlash issue. So this setup, it's just to give you a background, it's to be deployed in Western Australia. So there's like ocean currents going around here. So Sri Lanka is somewhere around here, and then the ocean currents go all the way and then through this path towards Victoria, and the around this tip, it's called Albany. The actual setup is being deployed, so it's a size of a building, and it's deployed here as a test setup in later this year. So that's with respect to wave energy power generation. We also worked with geothermal power generation. So this the geothermal power generation involves taking power of geothermal sources and then converting it to electrical energy. So Australia has like hot springs and then hot wells as well. So there's like water that you can heated low temperature water that you could take off the ground source and then use that, extract the heat or energy in that source and convert it to electrical energy. So that's geothermal power. So mainly the power generation works in a cycle called binary cycle organic Rankine cycle. So it's you have a working liquid that's a hydrocarbon. Unlike water, the working liquid, the hydrocarbon, evaporates at a really low temperature. So if you have a low temperature thermal source and you exchange the heat between the liquid water that's low temperature to the hydrocarbon. The hydrocarbon working liquid expands and then evaporates, creating a high pressure source that can spin a turbine. So this diagram that shows the process. So we have the geothermal well, water. Water is pumped through this heat exchanger or evaporator, and it so the blue line here that shows the working liquid. So that's a hydrocarbon based liquid. So that expands and then runs this turbine at high speed, and then it's condensed again, and then that cycle runs. That's a closed loop. The thermal source, that's brine or liquid, water that's at low temperature, passes through the heat exchanger and then back into the original source as well. So the high-speed turbine can be coupled to a geared machine, or it could be run direct drive as well. So that this type of application, in contrast with the other applications that we looked at in the previous slides, is slightly different, because now you have instead of a low speed rotating motion, you have a high speed turbine, and you want that to be stepped down into a speed that can be coupled to a generator or a low speed generator. So this is just an animation of the working principle of the geothermal power generation. We have the red liquid coming in here. That's the low temperature water coming in from the thermal source, and then it passes through the heat exchanger, and then the heat is the yellow liquid, that's the returning liquid. The blue liquid here is the working hydrocarbon that passes through the heat exchanger, and then it expands and then runs the high speed turbine. So that's pretty much the process in abstract. So that's the expanded hydrocarbon running into the turbine, and that spins the high speed generator. So this is one of the designs that we did for one of the companies that do that work with the geothermal power generation. So the machine that we designed was a direct drive. It didn't have a gearbox, so the machine needed to run at 45,200 RPM. So that's really high speed, and the generator was to produce 200 kilowatt. So since it's running at really high speed, the packaging or the size of the machine was really small. So you can see that it's nearly like 2 feet wide, the length of the machine, and then the diameter is about a feet. So the challenges of this type of generator is that due to the high speed, the bearings were very prone to require maintenance, and then the bearings are very expensive as well. They need like specialized bearings to run at that high speed. Most of the bearings, they're called like foil bearings. They run on a layer of air, and it's not, you don't have grease or anything. It's running on an layer of air that spins around the foil. So it's a really complicated technology for the bearings, and then that adds cost to the generator. Whereas if you were to run a direct gear drive, where you have a gearbox that steps down the speed into a manageable speed, such like 3,000 RPM or something like that, then you would have a lower cost option. but then the machine that you would need would be large, fairly large compared to this type of size. In addition to that, when you run the machine at high speed, we need to design the rotor, need a specialized design for the rotor. So this is a permanent magnet generator, and you can't actually see the permanent magnets. It's you need to have a cylinder, like a compression cylinder that holds onto the magnets. When it spins at that speed, the compression cylinder needs to balance out the centrifugal forces of the magnets. So that's a critical issue with designing high-speed machines. And also we have rotor dynamic issues where because of the high speeds, the natural frequency of the rotor kind of aligns with a certain range of speeds that we would be running the generator. So if it's a low speed machine, for example, the generator would be running at 3000 RPM, and the natural frequency or the speed at which the natural frequency occur might be like 20,000 RPM, and you would never be running at that speed. However, when you go into high speed machines, you would be running at 20,000 RPM, where the natural frequency of the machine, where it starts vibrating, is also the same as the speed at which you are operating. So there's a rotor dynamic or natural frequency issue that becomes critical when you're running high-speed machines. So that's another critical issue. Yeah, so in addition to this, designing the machine, we also looked at power, taking power off the generator. So since it's running high speed, the frequency, the fundamental frequency of the generator was above 1000 RPM, sorry, 1000 Hertz. So for example, a low speed machine might be running at 50 Hertz or 30 Hertz, between that range, whereas the high speed machine, the fundamental is above 1000 Hertz. So you need more high power electronics or specialized power electronic converters to handle that kind of fundamental frequency. In addition to that, the safety is also was a key important factor, because if there's a fault, then since it's spinning at really high speeds, the risk of a component, let's say, dislodging and then flying away from the system, that acts like a bullet going really fast out towards you. So there's a health and safety issue as well. So then if there's a fault, then we need to bring it down or break the generator really fast. So for that, you need to have braking resistors that can capture the energy very quickly and then spin it down or break the generator really fast, without if there's a catastrophic failure or if there's a fault signal. So that type of work we did for this project as well. So that's pretty much it, describing the direct drive machines and the applications that we worked in here in Melbourne and also Western Australia. If you have any questions, we can discuss now.
Yeah, thank you, sir. So if you have any questions, you can put them in the chat box, or also you can unmute yourself and ask the questions directly so that Dr. Nuwantha can answer them. Okay, I think we have two questions. I think the first one is, until other questions are coming up, I will just ask the first question from Gayan. It asks, how much would it cost for the 200 kilowatt high speed permanent magnet generator. Any comments? Yeah.
Yeah, so that's from just a rough estimate, it costs about 20,000 Australian dollars. So that's like you have to multiply it by 200 to convert it to rupees, or maybe around, let's say, 15,000 US dollars, maybe.
Mhm.
But that's with like prototype. But if you're like looking at assembly or mass manufacturing, then the cost reduces as well.
Okay, I think it might be helpful. So the next question is from Koshila Chandrasena. I think she's asking kind of advice. So she's asking like, I'm trying to start a research on renewable energy generation. If it is possible, please ask her to give his ideas to areas a student can focus.
For a research, you mean?
Yeah, so yeah, for a research based on renewable energy generation, renewable energy generation.
Yeah, so if always the alternative sources are interesting. So wind power has been researched quite a lot. So and then there's commercially quite a lot of effort to develop wind turbines. And as a research topic, I think wind power generation is maybe saturated. So you might be able to look at when for really higher power applications of wind turbines or wind power generation, how the machines would be designed. So there's alternative renewable energy such as geothermal power generation, which hasn't been, it's not predominant in industry or in application as wind turbines. So there's much more research that you can do with other alternative technologies as well.
Yeah, thank you, sir. So there are two questions from Mr. Parakrama Jayasinghe. The first one is any comments on the use of direct drives for steam turbines used for biomass power plants? And the second question is how would the direct drive work with vertical axis wind turbines?
Yeah, so the application of direct drive machines from experience, it kind of depends on the scale, the power level as well. So if it's, for example, a low power 10 kilowatt or 20 kilowatt type of system, you could benefit from having a permanent magnet machine. Whereas if it's really in megawatt scale, if you're going above 1 megawatt, then it might be beneficial to have a geared, like synchronous generator type of setup as well. And the application also depends on the speed at which it spins. So for example, we saw that for low speed hydro turbines, you have a low spinning, high torque shaft, whereas for geothermal power generation, we have a low torque, high speed shaft. It's easier to, couple the high speed shaft to a electric generator directly, and then have a high speed machine directly generating power. Whereas if it's a high torque, low speed machine, you would need to have a gearbox to spin, to convert that speed into a higher speed and connect it to a lower size generator as well. So it depends on the speed and torque profile as well as the power level as well. And in relation to the vertical axis wind turbines, then in wind turbines, one of the critical issues is the construction of the setup, where we have you need to place a high weight on top of a structure, and the stresses on the structure itself need to be considered when you have a heavy weight. So if you have a vertical type setup, if you have a geared option, and if that weight can be distributed easily among the pole structure, then that might be better rather than having a direct drive option as well.
Yeah, thank you, sir. I hope you answered his questions, and if there is any other questions, please feel free to ask it here, or maybe put them in the chat box. We can wait for few minutes. Yeah, I think seems like that's it. So thank you, sir. Thank you very much. Now, I will invite Dr. Akila Wijetunga, the chair of IEEE Sri Lanka chapter, to present the vote of thanks.
Okay, thank you so much, Dr. Nuwantha. And it was like very practical, and also as we are moving towards this energy transition, these are the changes we are expecting in technology, and that is very helpful for even students and as well as the professionals. I think the audience got the best out of it. And the question shows like how much interest and also the content that you delivered is very important for future renewable energy integration. Thank you so much for taking your time. And also, I hope we can keep continuing. And if there are any opportunities for either students or professionals to get engaged with these kind of research, it will be helpful if there is any opportunities for Sri Lankan and even other countries. So thank you again on behalf of IEEE Power and Energy Society Sri Lanka, as well as we have ISL sectional committee chair as well, Nuwantha. I saw him around. So I thank you on behalf of both committees and hope to get more content from you in future regarding this power sector development.
Yeah, thank you very much, Akila. Yeah, it's my pleasure to present the work we do here.
Yes, actually, that is the idea. Even from ISL also, they wanted to get this knowledge that we are doing in global level, how we can get connected with those kind of technologies to improve our knowledge and get along with the global trends. Thank you so much for that again.
All right, thanks.
So, again, thank you, Akila, for correcting us with the resource person as well.
Okay. Yeah, okay. Thank you, Dr. Akila. So thank you, Dr. Nuwantha, and for joining with us. And thanks all the participants for joining with us today. I hope we can see you all again in next webinar, hopefully very soon. Thank you very much for joining with us. See you.
Thanks. All right, cheers.